Good afternoon, ladies and gentlemen. I'm going to talk about our application of genetic algorithms and, or more generally, application of evolutionary algorithms for a interesting problem of optimal design of production areas layout. So first I will go through a motivation which is I think clear, but still. Then I will briefly, informally define the facility layout problem, which is the problem, how is it called in literature. And then I will describe our own formulation of the problem. And finally, I will illustrate, I will describe our approach, evolutionary based approach, and illustrate some results that it can provide with. So I start with this picture, which I hope clearly illustrates the fact that the optimal layout of facilities is one of the most important problems in production management and industrial engineering. Good layouts contribute to overall efficiency of operations and can reduce total operation costs. On the other hand, inefficient layouts can lead to bottlenecks, congestions, and poorly used space, and work underway can accumulate at some job posts, where if the job posts become idle or overloaded. So therefore a systematic way to automate the process of optimally design the production space layout should be a key part of the production management, production facility design and management. Not mentioned yet. So the physical layout requirements change for several reasons. Reasons related to Industry 4.0 with integrated cyber-physical systems. Other one is more and more demanding market requirements with a large portfolio of products and small production batches, where the typical situation where the production layout should be optimized, either updated or completely rebuilt, is when a new product is added to the production product portfolio, or when the demand is okay. Thank you. Or when the demand is seasonal, so depending on the season, one portfolio is active and the other one is inactive, and we need to switch between. So we need to switch between also plant or plane layout. As I said, this problem is formally defined in literature as facility layout problem, where the facilities can be either workstations where we try to optimally organize tools and machines within a single facility, or we want to organize the production lines within a production hall, or up to the highest level where we need to optimize the placement of buildings within factory premises. Generally, the criterion is that we want to maximize the space utilization, and the other most frequently used objective is that we want to minimize the material and product handling costs. Given some constraints such as no two entities can overlap with each other, which is obvious. Other constraints are, for example, facility infrastructure constraints, technological constraints, and so on. There are many FLP types differing in whether we just update existing layout, or we rebuild it from scratch, whether the entities, whether we consider just 2D or 3D version of this problem, whether the entities are regular or irregular, meaning that we can deal with rectangular shapes for simplicity, or with any other rectilinear shapes, or even free shapes. Another variant is when the entities are approximately equally sized, or if they differ in the sizes, and so on. So there are many variants of this FLP problem. In general, FLP is a very hard optimization problem, meaning that there exists no exact algorithm that provides us with a optimal solution in a reasonable time, where the reasonable means in polynomial time with respect to the size of the problem. So even that there are some exact approaches based on mathematical modeling, they are applicable only for specific variants of the problem, and they are efficient even for very small instances of FLP. So that's the reason why we often have to resort to approaches based on some heuristics or meta-heuristic methods, such as those ones, and especially evolutionary algorithms are very often used for these type of optimization problems. So I approach to our approach. First, I describe the particular formulation of our problem, meaning definition of production area and the elements, in this case workstations, and then I will describe very briefly the evolutionary algorithm itself and show some results. So we deal with the problem where the production area is defined by a rectangular envelope within which we can define some obstacles, the black segments, and communications, the gray ones, so that the whole area can be, in the end, can be very complex. And we want to place in the production area workstations, where each workstation is, again, for the sake of simplicity, defined as a rectangular area with some handling regions or handling areas attached to some site, one or two sides of the effective working area of the workstation. And then we define the orientation of this rectangular shape with which the workstation is placed into the available production area. So these are just formal constraints, such as no two workstations can overlap with their working area. No workstation can overlap with another, with its working area, with another workstation's handling area, and so on. And then the evolutionary algorithm, and then we use the evolutionary algorithm to solve this optimization problem, where the evolutionary algorithm, contrary to mathematical modeling approaches, is really meta-heuristic, which is, in this case, bio-inspired optimization meta-heuristic, where the algorithm really evolves a population of candidate solutions, where each candidate solution, these white rectangles, each of them is one candidate layout. And at the beginning, the layouts are just randomly generated, and through the iteration process, through the evolution of this population, where there are several operators applied in sequence in each iteration, such as selection, crossover, mutation, replacement. So through this simulated evolution, the population permanently improves until some point where user says, for example, okay, it's enough. The best solution currently in the population is good enough for me, so I stop the computation. So that's one of good points of this meta-heuristic, because, as I mentioned, mathematical modeling approaches, you model the problem, in this case FLP problem, you run the computation and you wait till the computation finishes, because there are only two options. Either it finishes with the optimal solution, or you wait for years till the algorithm ends. So contrary to that case, this evolutionary algorithm can be stopped at any time, and we can use the best solution currently present in the population of candidate solutions. So that's nice on this technique. And there are many variants how to represent the candidate floor plans into the representation on which the selection, crossover, mutation operators work. Yeah, so it's kind of art, or not art, but it's the engineering work that one has to do in order to make the evolutionary algorithm really efficient for the given problem. So in our case, we choose for an indirect representation, meaning that we evolve vectors of those elements, where each element says which workstation should be processed, in which orientation should be added to the floor plan, and which low-level heuristic is used to place the particular workstation into the layout. So I forgot to say that So this is, let's say, prescription how to fill the available area with the workstations. This is the prescription. This is the instruction list how to add workstations one by one into originally empty area. So these are the candidate. This is one of the candidate solutions, and candidate solutions like this are evolved within the iterative evolutionary process. So as I said, the workstations are added to the area, to the production area, according to this instruction list, in a way that there are some insertion points at each point of the evolution of each point at each point of the construction process, and given a new workstation, it is added into the currently optimal position within the developed layout. Yeah, so the workstations are added one by one into the floor plan. So this is the global picture. This is again the priority list, which says that this workstation is added first. So it is added at the top left position because it's at the beginning the area is completely empty. So this is added there, this is inserted there, the green one inserted there, and so on till the last three, which are those workstations. And this is one particular. This is a final layout represented by this particular candidate solution, and these solutions are evolved by selection crossover mutation within the evolutionary algorithm. We can, when I say optimization, that this is a optimization problem, so one can devise many optimization criteria. As I said, the most frequently used are make the floor plan as compact as possible. In other words, place the workstation within the area so that there is as much as possible free space remaining for example, other workstations that will be added in the future. The other criterion is, since the workstations are not independent, obviously, there are many interdependencies between workstations. One produces something which is the input for another workstation, and that produces products which are inputs for another workstation, and so on. So there are many dependencies between workstations. So the other criterion can be minimize the total length of all communications between dependent workstations. And what's also very important on the evolutionary based algorithms, that they are really suitable for multi-objective optimizations, which means that we can optimize, we can look for an optimal solution to the given problem, not only with respect to a single objective. We can optimize multiple objectives simultaneously in one run, meaning that in the end we are given a set of in this example, we optimize with respect to those two criteria. We want to maximize free space, and we want to minimize connections between the workstations, which is in most cases which are two objectives that are contra or competing to each other. Yeah, either you optimize one and you worsen the other, or vice versa. So this is illustrated in this figure, where this is, let's say, the result of one run of the evolutionary algorithm, where the algorithm provides us with a set of best solutions. And now there is really a set of best solutions, not a single one, because each one is better than the other ones with respect to one objective, and it's worse with respect to the other objective. Yeah. So then, for example, an expert in the field can explore those solutions and say, okay, this one is really the best because it has such and such characteristics which were not considered during the optimization process, but the expert sees that the one is the best for some reason. Yeah, so that's also advantage of this approach. Okay, let's skip this. And this is a snapshot of how the results look for our data set. So this is the this is one of the one of the best solutions obtained for the objective maximize free space. This one, this is the free space, so we want to maximize it. But it's let's say optimal with respect to this objective at the cost of not very good performance with respect to the communication costs. As we see, there are many long connections between dependent workstations, which in fact makes this solution not really usable. This one is solution when we minimized for the minimum connection costs or minimum transportation costs. We see that there is not much free space at the bottom, but the dependent or connected workstations are placed close to each other, which makes this solution even, in fact, in the end, even better than the first one. And this figure illustrates the situation when we run the multi-objective optimization. So we optimize both criteria simultaneously. We end up with this, which is called Pareto front, where all of these solutions is optimal with respect to those objectives we use for the optimization, but then the user can make his own decision on which one is really the best one we want to use. So at the one side there are solutions which are really good in terms of the maximum free space. On the other extreme of this Pareto front, there are solutions which are the best with respect to minimum connection distance. And if we know something about the background of the production line, for example, I mean, if we know detailed information about what workstation should be close to what other workstation. We can use this connection tree in a way that we run the layout optimization process in iterations. In each iteration, we add just certain class or group of workstations, and we add them optimally with respect to the space restrictions. So we add them in a way that the final layout after the group of workstation was added. So the layout is optimal with respect to the compactness requirement. Yeah, so if we do it iteratively, we see that in the end, we end up with the layout which is well performing with respect to the compactness or with respect to the criteria that we want to minimize as much as possible of free space, and as well almost all connections between dependent workstations are short as possible. And one final incremental modification of this approach, that for some time we may solve the FLP problem such that there are multiple possible choices how to implement each workstation. I mean, how to design the workstation space, how to organize tools and machines within the workstation. So either we can do it using space of size 375 or smaller size. Simply this picture should have illustrated that one implementation is smaller but more costly, and the other one is larger but cheaper. Yeah, so in the end, we are solving the problem where we not only have to place the workstations into the available area optimally with respect to the given objectives, but we also need to choose which variant of each workstation should be used. Yeah, either the smaller one and more costly, or larger one and cheaper. So this figure illustrates the fact that in the end, we this dashed line shows the cost of the solution obtained with a static setup, meaning that we have just one variant for each workstation. So if we find the optimal layout, its cost is such and such. If we run the same algorithm with workstations variants available, we get much cheaper solutions of that are also well performing within the maximum free space objective. So we get highly compact solutions which are cheaper than the solutions obtained with the static setup. And that was the last slide. This is just to conclude that I just presented a evolutionary algorithm for solving the optimal facility layout problem, which serves this should be stressed, which serves as a design support tool, meaning that it provides the user, it provides the expert with a set of candidate solutions, well-fit, well-performing solutions, from which the expert can choose in the end really the best one. It's suitable for many variants of the FLP problem. It can deal with multiple objectives simultaneously, and it can be even though I illustrated it on the rectangular shapes, we can easily extend it to free form, rectilinear, more complex